3.
Hello! We're about to review 3 different physics problems involving thermodynamics. First up, problem 37. The first thing I will do is just read the problem in English. A smoothly moving piston was attached to a cylindrical container shown in the figure, and a fixed mass of gas was sealed inside there. Initially, the temperature of the gas in the container is 27 degrees Celsius, and the volume is 2.0 times 10 to the third meters cubed. And the pressure is 1.0 times 10 to the fifth pascals. Now, let's write down that information. First, we have temperature equals 27 degrees Celsius. We have the volume equals 2.0 times 10 to negative third meters cubed. And we have the pressure is equal to 1.0 times 10 to the fifth pascals. Now, what is number 1 asking from us? When the cross-sectional area of the piston is, let's write that down, area is 0.25 meters squared. Find out the magnitude of the force of the gas container pushing against the piston. Now, this is actually a very simple problem based on our knowledge of pressure and forces. You see, pressure is really just force over an area. Now, we're looking for the force. So let's use algebra to rearrange this. Force equals pressure times area. Therefore, force equals our pressure times our area and that gives us our final force of, let me check my notes, that's right, 0.25 times 10 to the fifth newtons, which can be rewritten as 2.5 times 10 to the fourth newtons. That's problem number 1. Now, problem number 2 asks us something else. When the gas in the container is compressed by pushing the piston, the volume of the gas changes from its initial state to a smaller state. That smaller state, I'm going to write as V final. The new volume is 1.0 times 10 to the negative third meters cubed. And it has a new pressure. That new pressure, which I'm going to write as pressure final, you could also write this as P2 or P prime, all are acceptable, is 2.2 times, let's see, 2.2 times 10 to the fifth pascals. Now we need to find what? The question is asking for what is the new temperature of the gas. Let's write that as T prime. Now, in order to do that, we're going to use the relationship of a closed system. A closed gas system. The initial pressure and volume over the temperature is equal to the final pressure and volume, we'll use primes here, over the temperature. All we have to do now is put in our values. So our original pressure was 1.0 times 10 to the fifth. Our original volume is 2.0 times 10 to the negative third. Now this is important. You may think, oh, our original temperature is 27 degrees. No. You're missing an important fact. Whenever you use any of these relationships, you need to convert from Celsius to Kelvin. So this is not 27 degrees Celsius. This is 27 degrees Celsius plus 273, which will, of course, bring us to Kelvin. All right, the left side is good. Let's look at the right side now. Let's see, our new pressure is right here, 2.2 times 10 to the fifth. Our new volume is right here, 1.0 times 10 to the negative third. And this is all over our new temperature, which is what we're looking for. Now don't make the same mistake twice. We are looking for the new temperature, but we're going to have to deal with that extra 273 degrees. So I'm going to make this as little t. This is our little t. We sometimes use little t for time, but for this I mean the temperature without Kelvin. Now, I will save you all the math of doing all this out. Move this up here, move that down here, move that up here. Once you do all of your math, you're going to find that T prime, this thing, is equal to little t plus 273, which is equal to math, 330. We do our subtraction now to find that our new temperature is equal to 57 degrees Celsius. And that is how you do problem 37, parts 1 and 2. All right, now we're going to tackle problem number 38. First, I'm going to read the problem in English. Container A of 0.10 meters cubed and container B of 0.20 meters cubed are connected by a thin tube, and hydrogen having a temperature of 27 degrees Celsius and a pressure of 1.0 times 10 to the fifth pascals is put into the container. What is the pressure in the container when the temperature of B is 127 degrees Celsius, while keeping the temperature of A 27 degrees Celsius? Also, how many moles of hydrogen moved through the thin tube by changing the temperature conditions. Thankfully, we can ignore this volume of the thin tube. And we can also say that our gas constant, I think I can use big R for this, 8.3 joules per mole Kelvin. Now, this problem is asking for two things. The first thing it wants to know is it wants to know what the new pressure is. We had the original pressure back when everything was 127 degrees, but now we have a new pressure because we raised the temperature of B. Now, let's work on that. In order to do this, I think the most effective way is to count the number of molecules on each side before and after. This will help us solve both parts at once. Now, excuse me. For our original side, the amount of molecules in A and A, then we have the amount of molecules in B and B. These are before, and then we have after. Now, what are all of these? Well, we're going to use the relationship PV equals nRT. PIVNRT is sometimes the acronym we use in America, but PV equals nRT is how we say it. Now, first let's find NA. For all of these, we're going to solve for N. N is just PV over RT. So for N here, we have our pressure, 1.0 times 10 to the 5th, times our volume, 0.10 times 10 to the negative third, no, yeah, 0.10, over 8.3 times, and this is important, 300. Where did that 300 come from? I don't see 300 on this board. Well, the 300 came from the 27 degrees Celsius plus 273 to get 300 degrees Kelvin, because we have to use Kelvin. Now, I'm going to help set this up because NB, NA prime, and NB prime follow a similar pattern. So I'm actually going to rewrite this to make it easier. What I want to do is do NA plus NB equals NA prime plus NB prime. Pardon me. Let's make those capitals. This must be true because this is a closed system and no gas will escape that system. So the amount of molecules before must equal the amount of molecules afterwards. Alright. The process for these is all the same. So let me just walk through those real quick. That is 1.0 times 10 to the 5th times 0.10 over 8.3 times 300. Great. NA down. NB is very similar. In fact, it's the same, except the volume is different. As 1.0 times 10 to the 5th times 0.20 over 8.3 times 300. This side gets a little tricky because we don't know the pressure. We're trying to find it. So I'm just going to put pressure. So we have the pressure times the volume of A, 0.10, over 8.3 times, well, 300. The temperature is the same. Same process over here. The pressure is the same because since these are one system, the pressure has to be the same throughout, times 0.20 over 8.3 times 127 plus 273, 400. Now, this is a lot of math, but thankfully it's very easy math. There are two things we can do, but the first thing I want to do is just solve for pressure. This is that pressure we were looking for in the beginning. When you do all of the math and all of the algebra, which basically consists of move those over there, move those over there, divide, divide, you're going to get a pressure equal to 1.2 times 10 to the 5th pascals. Because all you have to do is solve for P prime. Now, last thing we have to do is find out how many moles of hydrogen moved through the thin tube. Let's take A. The amount of molecules in A at the beginning was this number. That is 4.01. 01 when you solve that. This here is Na prime. Ooh, so bad. And all we have to do is now we have the pressure. Put that pressure in. Boop, 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 boop. 4.81 moles. To find out how many molecules moved, we just have to subtract. Na prime minus Na equals 0.80 moles. And that is how you solve problem 38. Last but not least, we have problem 39 that involves this diagram. Now, I'm going to read this problem in English first. Answer the appropriate phrase or expression that goes into the blanks of each sentence. A gas molecule with mass m is moving to the right at velocity v, and the molecule is repelled by a vertical collision, an elastic collision, with the square wall side length L. The impulse the wall receives from one molecule is the size of blank. Well, we know that before the molecule is moving in, mass m, velocity v, And afterwards, if this is like a before, afterwards, the molecule was moving in that direction with velocity v. But it's moving in the opposite direction. So let's write that as negative v. So how much impulse did this molecule have? Well, impulse is the change in momentum, which is, let's see, our final momentum is negative mv minus our initial mv is equal to negative 2 mv. Okay, but that's for the molecule. The wall must have an equal impulse, but in an opposite direction. So this wall's impulse is 2 mv, and it is to the right. We also can say it's to the right because this is positive, and we have said that right is positive and left is negative. So that answers, I believe, E and A. So now, let's look at U. It is assumed that n gas molecules collide with the wall per unit time. Since the magnitude of the impulse that the wall receives during the time t is, let's think about that. We have this amount of impulse per molecule. So if we have more molecules, we'll have more impulse. And if we have more time, we'll have more impulse. So let's say that the impulse, change in momentum, is mv, 2mv, times nt. Because for more time and more molecules means more impulse. Now, the last question is, what is the pressure the wall will receive? This is the pressure. Well, I remember from an earlier problem that pressure is equal to force over an area. So how do we get force? Well, impulse is just equal to force times time. So, therefore, our force must be, cancel out the t's, 2mnv. Okay, let's take that and put it down here. 2mnv over what? Well, thankfully, this is a square, so its area is pretty easy. That's just L squared. And this is your answer to D, right here. Alright. I believe that covers all of 39. E, A, U, and D. I hope that helps, and I hope that explanation, while maybe quick, gives a stronger connection of how physics and English can be connected. Thank you.